Great, thank you. I'm very excited to be part of this warm-up, and I'm looking forward to meeting some of you in person in Boston at my workshop on mapping geospatial data in R. So what you see here is the GitHub repository for the entire workshop, and as part of that, I have the materials that I'll be using today. So if this is something of interest to you, I think that that link is going to be put in the chat window so that you can grab that. You can take a look at the R code, follow along with us, save it for later, and also get a sneak peek at some of the things that you may be able to experience in Boston in my workshop. So as Alvaro said, my name is Joy Payton, and I'm a data scientist and a data educator at the Children's Hospital of Philadelphia. And I work with all kinds of data related to human health. And one of the things that I find really interesting to work with are what we call the social determinants of health. These are things like poverty, proximity to safe public parks for children to play in, maybe pollution in a neighborhood or crime, basically the socioeconomic realities of a person's life. And we know that these affect health, so they're important to us at Children's Hospital. And a lot of times our patients and our research participants experience what we would call an environmental exposure that's geospatial in nature. For example, a child goes to a school that has asbestos, or a child grows up near a freeway, or maybe a child's neighborhood experiences lots of violence. And this is what really spurred my interest in mapping geospatial data in R. R is the environment that a lot of our physicians and researchers use. And it's a great way to be able to do all of your analysis in R and not offload some of your analysis to an expensive, potentially, and very specialized GIS software package. So just to set some expectations here, I will disclose I'm not a geographer, I'm not a demographer, I'm not an expert in Esri or ArcGIS or cartography. But what I do want to be is an expert in helping scientists find and communicate their research findings in the most effective way possible. And I think maps can do that in a lot of cases. So today I'm going to share some of what I've learned along the way working with researchers. And again, just give you a sneak peek of what you might learn with us in Boston. So did that link get posted, Alvaro? Oh, there it is, perfect. All right, so another quick disclaimer. What you see here is the R code. And in this R markdown file, there are a few libraries along the way that if you are not accustomed to using mapping software or geospatial software or packages, you might have to install these. But these are all libraries that are hosted in CRAN. There's nothing bleeding edge in this presentation that you would need to get from GitHub, for example. So we begin, as we do often in data projects, with some interesting data. So in this case, I'm taking this file from the City of Philadelphia Open Data Portal. And a lot of you, wherever you're from, if you're in a state or locality that has an open data portal, you'll have files like these available to you. So in this case, this is a file that has information about blood lead levels in children. And it's a GeoJSON file, so a lot of us are used to using JSON. And this stores geographic data in a JSON format. And when we pull that data in, you'll see, we'll go into a little bit more detail about what this contains. And there's other types of files out there, like shapefiles, which I don't have time to go into today. But for today, we're just going to stick with GeoJSON. So let me go ahead and pull that in. And while we're waiting for that, let me just point out, this is just a good citizen policy. Whenever I hit any sort of public server, I always like to put cache equals true, because if I'm going to rerun my R markdown file several times, I really don't want to hit that server multiple times. But that can throw some problems your way when it comes to mapping, in case your maps get cached. So just an FYI, if you try this at home and you realize that your maps don't look right, try clearing your cache. Just delete those cache files. So we have this data pulled in, and we're using the library RGDAL, which is going to basically take any sort of format of geospatial data and make it uniform. And what we have here is we have a data frame that it's just a traditional tabular data set, and it has data about the geography that's contained in this file. So if we just take a look here, let's take a look at the tabular data. So this is the first 6 rows of our tabular data here. And in the data portal of the City of Philadelphia, there's a lot of information given about the provenance of this data and what it means. But essentially what we have here is a listing of census tracts in the City of Philadelphia. And in each tract, a certain number of children were screened. That's the num screen here for high blood lead level. And if the number was 0 children or 6 or more children, that number is listed in the number here. And then from the numerator here, the number who tested positive for high blood lead, and the denominator, the total number who were screened, obviously it's very easy to arrive at a percentage. Well, what is this data redacted here? So if the number of children who test positive for high blood lead is between 1 child and 5 children inclusive, that number is suppressed. And that is in order to maintain what's called K-anonymity. And this is used widely in human subjects research and public health. K-anonymity in this context is the idea that if a number of patients affected is too small, it might be easy to ascertain who they are. So in this case, I think that's an abundance of caution. I think that's being maybe overly careful, but that's what we have here. So just keep in mind when we have this redacted data and we don't know what the numerator is, we know it's 1, 2, 3, 4, or 5. So we could potentially do some imputation of data here. And it wouldn't be a wild guess. We do have some parameters as far as what the measured percentage would be. And the statistical summary I'll leave for you to look at offline if you're interested. But I will point out here that the max of our percent of children affected with high blood lead, which is 5 micrograms per deciliter or more, is almost 18% in one of our tracts. And that's disturbing. That's something that we care about as far as child health is concerned. So I said before that GeoJSON and really all of your geographic objects contain geographic data, not just tabular data. So we can display the map using this great package called Leaflet. Now, Leaflet obviously is not the only data visualization game in town. And in the workshop in Boston, I'll be talking about other ways to create maps, especially using ggplot2 for those of you who like that package. But Leaflet is really great for very quick and dynamic maps. By dynamic, I mean you can pan and zoom, and they really don't require a lot of syntax. So just a little bit of background as to what this code is doing here. What I'm doing is I'm setting my view. In other words, where is my map going to center and how big is it going to be? I'm setting the view to the center of the bounding box. So just really quickly, let's do a structure on Philly lead map. And I'm going to do max level equals 2 so we don't go too deep into the weeds. And you can see that we have data. That's that rectangular data frame. We have 380 shapes or polygons that represent census tracts. We have this plot order, which basically links the polygons to rows in the data frame. And then we have this bounding box, which is the corners of our map. So I want the center of my map to be in the center of that box. And this zoom level is honestly a little bit of trial and error. So I set it at 11. And then I'm going to add the polygons. So let's see what that looks like. All right, so that is not the most attractive map I've ever done. The defaults are not terribly exciting. And what's more concerning is it looks like we have some holes here. There's a hole towards the north end of Philadelphia. There's a hole down here kind of towards the south end of Philadelphia. And what you can't really tell is that this curve over here is also a census tract. So we've got, oh, and there's one right there. So we've got 4 missing tracts. And we would really like to look at lead across the board, across the city of Philadelphia, and we want a complete map. So if we want a complete map of Philadelphia, what I'll do is go ahead and go back to my data portal, and I'm going to get the actual census tracts for the city of Philadelphia. So again, it's a GeoJSON. So when I run that, all right, you get these nice notes, by the way. So 384 features or polygons. So that has every single census tract, the 380 from before, and then the 4 additional that we're missing. And it has 14 fields. So let's take a look just at the tabular data that is with this census map. So this seems to maybe be a little bit of overkill, the amount of data that we have here, because we've got tons of codes and labels that describe the 384 census tracts in Philadelphia. So we have this state FIPS code, this county FIPS code, and the tract. And then together, you can just concatenate them and get this. And then if you just lop off these last 2 numbers, the name of the tract is tract 94. And then you've got this pretty print version that's human readable. So you get the idea. And sort of like where in space these are. It's got a latitude and longitude. All right. And I'm just going to expand this a little bit. Excellent. And I want to bring your attention to this thing called object ID. An object ID is simply, it's like a row number. It goes from 1 all the way up to 384. And that seems almost trivial, but this is going to be very helpful for us. And this is very important for you to remember if you're ever going to combine data from various sources into a single map. You need to know how to maintain your row order, because the polygons in my object are separate from the tabular data. And the polygons count on the tabular data maintaining its order. And the order of rows can get messed up very easily when we merge data. So it's very handy, and I would say even essential, to have a column here that simply goes from 1 until the number of rows that you have, essentially like a row name. And if we didn't have object ID here, we would have to create it. So that seems like a very trivial variable, but it's actually quite useful. So let's just take a look at the map of this and see if it is a full map. All right. First of all, do we have 384 rows? Yes, we do. And I'm going to map using leaflet again. So similar to what we did before, I say leaflet and the name of my object. And then I set the view as we did before, with the bounding box being the center, and a zoom level that I established by trial and error. And I use the add polygons, which is what I did before as well. But I'm putting all this other stuff in that's new. And if you remember, our first map was blue and kind of fuzzy. It wasn't very attractive. What we're doing here is setting those colors, and we're also adding a label. And this is a fun and really useful add-in that comes with leaflet extras, and it is suspend scroll. So if you've ever scrolled on a website and accidentally scrolled inside the map instead of past the map, this is intended to stop that. So let's see what this map looks like. So we can see that getting away from the defaults, it's a much more visually appealing map. And okay, I can zoom in and scroll. All right. And we don't have any holes here, right? So it's a complete map. So that is the geographic map that we want to use. You can see that it just said click or hover to wake. And that's so I can just sort of scroll up and down and not accidentally scroll inside my map. I have to kind of wake my map up in order for scrolling to affect the map. So this is a great map, and we want to pull in the data from our lead object into this object. Now, we established earlier that both of these maps, or both of these large spatial polygons, have a data frame associated, right? So the data frame associated with the full Philadelphia map is all this information about the census tracts. And in the Philadelphia lead object, all the data is about child lead levels in these various tracts. So we've got two data frames, so merging should be fairly trivial, right? And that's kind of what I'm doing here in line 100. I'm simply going to do a merge, and what I'm merging is the data frame from one map and the data frame from the other map. And the hinge, or the overlapping field, is named different things, so I indicate that. And I indicate all equals true, and I merge it. So I'm going to run just this bit first. And what I'd like to do is, let's look at the merged. And we can see, remember how the object ID earlier started at 1 and it went down all the way to 384? Now this is out of order. So we start at 190, then we go up for a while, then we make a big jump to 332, then 298. And that's because it looks like what merge tried to do is order it on census tract. It likes to order it on whatever your shared variable is. And that's going to break the link between the rows in my data frame and the polygons that that data is supposed to adhere to. So that's why I'm not going to just put that data frame back inside a map. I need to change the order of it so that it follows the order of object ID. So I'm going to reorder it. In fact, let's just take a look at what it looks like when I reorder it. All right, now we have an object ID that starts with 1 and increments, and that's what we want. So let me go ahead and run this line. So what I've done is taken my lead data and my census tract data and combined them in this full Philadelphia map. So now we've got a full map of the city of Philadelphia, and we've got this lead data, and we'd like to do what's called a Chopleth. So if you've seen those color-coded maps that show the intensity of a value by using either hue or color or intensity, that's what a Chopleth is. So I'd like to start by setting up a palette of colors. So I would like the colors that represent how bad the blood lead problem is in children. I would like those colors to be different shades of blue. And I would like to break up the blues into 10 different colors of blue, 10 different shades, that break up this value, the percent of 5+, which is the percent of children who have 5 micrograms per deciliter or more of lead in their blood. And if there's no value there, please just make it a shade of gray. So that's my lead palette. And I'm going to once again do a leaflet map. This is sort of what we've seen before, right? Except this fill color. Earlier, I just said fill color equals white. And now what I'd like to do is have a dynamic fill color so that the dynamic fill reflects wherever in this palette, whatever color should correspond to the lead level for this particular tract. And again, I'm going to add a label and suspend this scroll. So let's run that and scroll down. So when I talked about labels, I didn't really show you what those do. So what labels allow you to do is hover over a geographic feature, whether it's a shape, a polygon, a line, or a point, and get some information back. So that can be really helpful in your data visualization here. So we can see we've definitely got some hot spots of high lead in this neighborhood here. Maybe another hot spot here, down here. But we also have a lot of missing data. All right, so what are we going to do with all of this missing data? So we're going to do some imputation. So in part, we can use k-nearest neighbor imputation. And to do that, we first need to identify for each tract, what are the neighbors? So this code is essentially determining for each tract what its 10 nearest neighbors are, including itself. All right, so now we know for each tract, which are the nearest neighbors, right? So these are just a list of what the neighbors are for each tract. Now keep in mind, we have missing data for two reasons here. So we have missing data because in the initial lead study that was shared with us, there was some suppression of data. So if there was 1 to 5 children only who had high blood lead, that particular number, that specific number was suppressed. It was redacted. So we don't know the numerator. We do know the denominator. We know how many children were screened in that area, but we don't know how many tested positive. So we have sort of a good guess as to where this percentage will be. But then we have those 4 tracts that weren't in existence in our original data set. So we have no idea what those are. So we're going to do sort of a hybrid approach to imputing data because we've got a lot of data about this missingness. So let's just take a look here at the imputation logic here. So we're going to first do the imputation for the tracts in which we know it's 1 to 5 children. And so there's a few things that we could ascertain or propose from that data. We know that the lowest percentage of high blood lead is just 1 child over that number of children screened. And the highest possibility is 5 children. We'd like to do k-nearest neighbors to get a better guess because we know that lead exposure is very geographic. For instance, Philadelphia used to be very big in shipbuilding. So there's lead residue in our soil. So k-nearest neighbors make sense. We believe that neighborhoods tend to go together as far as the lead exposure. So we'd like to use k-nearest neighbors, but we've got these handy guardrails of the 1 child up to 5 children. So we'll do that imputation first, and that will populate all of our missing tract data except for those 4 that we didn't have any information about. So this for loop is a little bit complicated, but basically what I'm doing is saying for every tract that had data redacted, look at its 10 closest neighboring tracts and get the average of their rate of high blood lead. And that's a pretty good estimate. That's that KNN. That's a pretty good estimate. But we know that it can't be lower than the lowest percent possible, and it can't be higher than the highest percent possible. And if, for whatever reason, we can't calculate the KNN, we don't have enough neighbors to give us information, which could happen because we have large swaths of Philadelphia without information. We're just going to take the expected value of 1 to 5 and say, let's just choose the median of 3 children from that 1 to 5 possibility. So we're going to do that sort of imputation first. 4 tracts that were completely missing. And that's a great case for k-nearest neighbors because now we've got information all around the tract that's missing, so we can easily just take that average and do some somewhat naive KNN imputation there. So here I say remap that, John. So if you're not from the Philadelphia area, that's our way of saying whatchamacallit or doodad. So let's remap that, John. Again, this is the same code that we had before. We set up our lead palette and we're going to map this and we're going to fill our polygons according to the percentage of lead, that data point. But now we shouldn't have all that gray. All right, that looks pretty good. Okay. So again, we've got a couple of hot spots, right? But we've got a nice full map that is, partially from data that we obtained from the city of Philadelphia, partly with some intelligent imputation that we provided. And what we want to do now is enrich this with information about the economic and financial realities of our patients. We'd really like to enrich this with data from the Census Bureau. In my workshop in Boston, we're going to work a lot with Census Bureau data because there's a lot of data available. So we'll talk about how to select it, how to obtain it and reshape it, how to work with the Census API, and we're going to get into a lot of depth. I didn't really have the screen time today to go into that. So what I've done today is to simplify matters and just create a canned data set. So I've taken a sample of data about Philadelphia from the Census Bureau's American Community Survey. And I've renamed those variables to make them simpler and easier to understand. And I've saved them as a flat file, as a CSV. And that CSV is in the GitHub repo if you want to play with this. And you can get all sorts of data from the Census Bureau. Demographic data relating to race and ethnicity, cultural trends, computer use in the home, for example. How do people get to work? What are some language and migration patterns? Are people moving into an area or out of an area? You can get whether homes are rented or owned. There's a deep richness of data here. So I just chose a handful of variables that I thought might have something to do with the economic realities that might affect a neighborhood, like the percentage of families that fall below the poverty line. So let's pull this data in and take a quick look at it. So again, I have the census tract here. Obviously, that's our common data across all these data sets. The percent of unemployment, the percent of people who use public transit to get to work, the median and the mean household income, the percent of child lack of health insurance, and the percent of families below the poverty line. And that's something that we in Philadelphia really struggle with. We are one of the nation's poorest large cities. So this selected economic characteristics of our census tracts are going to tell us a little bit more about the social determinants of health here. So what we'd like to do is merge this in, and we're going to do the same thing we did, which is make a merge, and we're going to make sure that we maintain the order of the rows. So let's just do that. Great. So now if I look at the structure here of my full Philadelphia map, the data frame, that rectangular data frame that has information about the polygons, we'll see now that we've got tons of information. We've got this lead information, which was from our first GeoJSON file. And then we have all of these Census Bureau codes about census tracts that we got from our second GeoJSON file. And then we have these values that came from that flat CSV. And that's all now in a single place. So what I'd like to do is map information with some more useful labels. So we saw labels before that just were like the name, right? The name of the polygon. I'm going to use sprintf and interpolate some variables there. I'm just going to use these created labels that have several different variables: the name of the tract, the percent of families below the poverty line, and the lead percentage. I'm going to map that again. And here I'm just adding some label options to make it a little bit neater and more attractive. All right. So now if I hover, I can see more information, right? So I can sort of get more contextual information about these tracts. And as we're getting close to the end, that really doesn't show us the impact of poverty overall. Sure, it's in the labels, but we'd really like to see it in the map. So what I'd like to do now is have two layers. One layer is my lead layer, and I label it as lead level, and have another layer that shows poverty, and then allow users to choose what they want to look at. take a look at that. All right, this looks very similar to what we just saw. I accidentally zoomed. But now we can sort of toggle back and forth between lead and poverty. So I like to always ask, what is the so what of this? So what we've done here, it's not a rigorous statistical analysis, and we haven't modeled lead and poverty. And in a real scenario, we definitely want to do that homework before we went down the road of a particular data visualization. But what we have done here is create a map that conveys a lot of information about what's happening in the city of Philadelphia with fairly simple code and not a lot of time. And this kind of map is really great for policymakers, legislators, donors, journalists. Put it on your website. It's simple to understand, and it's easy for our stakeholders to manipulate. So I hope that this sparked your interest. There's a lot more to talk about as far as mapping data in R, and I'm really excited to be giving this workshop in Boston. So I hope I'll get to see some of you there. Thank you very much.